So as already mentioned, today's topic is 3D pattern transfer. That's about how to actually transfer the structures written in a resist with an NanoFrazor into some other materials. But before I go into all the details, let's revisit the feature of the NanoFrazor that Emine already referred to briefly. So the very high accuracy 3D patterning capability. That's based on the so-called closed loop lithography principle. So what happens during the writing with an NanoFrazor is that we have a hot tip evaporating the polymer from here, shown from left to the right, pixel by pixel. And then at the end of each line, the tip turns back from right to the left here in the image, and image is the same line. It just wrote with a cold tip in a contact mode, kind of an AFM image. And actually what it does, it then feeds back the measured depth data to the software, and there's an algorithm that adapts the patterning depth. So it compares the written depth to the desired depth and adjusts the force acting between the tip and the substrate accordingly. So if it's writing too shallow, it will add more force and vice versa. So this, of course, will decrease the total fabrication time. So we will have adaptation of the patterning every few milliseconds. So we will have a very good quality of the patterning from the very beginning on. And of course, as a nice side product, we always get a topography image of the pattern that we just wrote without having any additional effort at all. What is the nicest thing about it is that it enables us to pattern 3D patterns with sub-nanometer resolution in the Z direction. So for example, here on the left-hand side, we can see an example of a continuous sine wave written with an NanoFrazor. Here in the beginning, you can see when the feedback actually finds the right force. So the first couple of lines are not written correctly, but it very quickly adapts the force of the patterning. And eventually the rest of the pattern is written with less than 1 nanometer error in the Z. And of course, for the next written frame, it remembers the settings and it will look perfect from the very beginning on. On the right-hand side, we can see another example of a checkerboard with 16 discrete depth levels with 1.5 nanometer depth differences between each of them. And here, in this case, the error is less than 0.7 nanometers. And actually, this kind of patterns, I would say it's not possible to fabricate with any other existing technology, at least with such a small error. So here's an actual application example of 3D structures written in the PPA, our workhorse resist. So here on the left-hand side, we can see the surface topography measured by AFM of a cow's tendon section. And on the right-hand side, the same structure replicated in the PPA resist with an NanoFrazor. And this can be used for studying the role of topographical signals in cell matrix interactions. So we can actually study, for example, cell cultures on structures that resemble very closely the biological sample, but with maybe some additional features or with a different, with just the topography and not the other biological constituents. But actually, as much as we like PPA, we have to admit that PPA is not the ideal material for most applications, even it can be used for many applications already as such. But actually, we need to also be able to transfer the 3D patterns in other materials as well to make this 3D patterning much more useful. Now, the first technique I will present is reactive ion etching. It may be the most intuitive to most people involved in nanofabrication. It's a very commonly used technique, and also that's what we looked into first. The principle is very simple. So we have a layer of PPA that has been spin coated on a substrate where we wish to transfer the 3D patterns. Then we use the NanoFrazor to make the 3D patterns in the PPA. and then we apply suitable reactive ion etching recipe. So of course the gases and the parameters have been adjusted to match the substrate material in question. But actually, yes, I want to introduce a couple of small tricks that we use actually. So first of all, we won't be able to pattern to the very bottom, so we won't be able to remove all of the resist with the NanoFrazor, because the substrate acts as a heat sink and it cools down the NanoFrazor tip as the tip is approaching the substrate. So what we normally do, we apply a very thin PMMA layer between the PPA and the substrate. It's simply thinned down PMMA that has been spin coated and baked, and it acts as a thermal buffer layer, which actually allows us to pattern a bit closer to the substrate surface as if we only would have the PPA layer. And this allows us, of course, to reduce the reactive ion etching time, and also we will have a little bit less roughness and also maybe less contamination of the areas outside of the desired structures. Another thing that we can see here in the image is that we have actually a recess around the pattern, so kind of a frame that has been sunk a little bit into the PPA, and actually this helps us in finding the right etching time. So we don't have to stop the etching exactly where the top of the 3D patterns is, but we actually have a recess that is 10 to 50 nanometers deep, and we aim to stop the etching within the recess. So we have a broadened process window for the patterning. So ideally, this after ideal etching time has passed, so we actually have a little bit of residual polymer still remaining here, but all our pattern has been etched fully, and the polymer has just been removed fully outside of the 3D pattern itself. And actually, this will enable, enable us to then remove the residual polymer using a solvent, and we will have much less contamination than on the unaffected parts. So, for example, if we use a fluorine-containing gas, fluorine is notorious for leaving very difficult to remove residuals on the samples. And if we have still part of the sample covered with a polymer after the etching, we are on a good way to get rid of most of this contamination later. So let's have a look at a couple of examples. So here we have a 3D hologram pattern. So we have a 8-level computer-generated hologram. Actually, if you shine a laser on it, this is just the full pattern is seen here on the top. If you shine a laser on it, it will show the logo of the Swiss litho, the former Swiss litho. The total size is 10 by 10 microns and 250,000 pixels. And we should acknowledge Professor Dong, who kindly let us use his pattern. So we wrote the pattern then into the PPA with a NanoFrazor. It took 1 minute to write and also to acquire this image. Each of the levels were 8 nanometers deep within the PPA, and the total thickness of the PPA was 90 nanometers. Afterwards, the resist was used as an etching mask to etch the pattern into a silicon substrate using SF6 and C4F8. And in this particular case, we achieved an amplification of depth in the range of 10, in excess of 10 times. So the final etching depth was about 700 nanometers. And actually here we can see a pillar with aspect ratio of 11. So I would have to say that actually the amplification of 10 is on the upper end we can achieve using a PPA alone as the etching mask. Another example, our collaborators at KIT and EPFL have created such 3D phase plates for electron optics. So these phase plates can simply be placed within the electron beam in a transmission electron microscope, and then the electron passing through will receive a phase shift depending on the thickness of the phase plate. This can give rise to vortex beams. It can be used for aberration correction or super resolution imaging. How they were made? Well, first of all, the 3D pattern was written in PPA, as for the previous example. And in this case, the pattern was transferred using different chemistries into silicon, as can be seen here in the middle, and also into silicon dioxide and into silicon nitride. And finally, the backside of the wafer was etched with KOH to form a suspended and electron transparent 3D membranes that could then be inserted in the TEM. And here's a nice paper about it, published last year, if you're interested in more details. Now, the question arises, so what is the kind of maximum transferring depth for such 3D patterns that I have just shown? Well, let's have to understand that limitation. Let's have a look at one of the cantilevers in an SEM more closer. So actually, if we zoom into the very tip of the cantilever, here's the nose of the cantilever, and we can see that the tip is actually not located exactly at the nose of the cantilever, but there's a couple of micrometers offset. This is because of the way the heaters are designed and how the current is passing through within the cantilever. Then actually, we also have to approach the surface at a certain angle because we want to make sure that the tip will hit the sample surface first and not some other part of the cantilever. And actually, this gives rise to the maximum patterning depth, which is, depending a little bit on the length of the tip exactly and on the angle we are using here, but it will anyway be in the range of less than 250 nanometers. And as I already mentioned earlier, the selectivity we can achieve using PPA alone as etching mask is maximum 10, about that. So we get the maximum, very maximum depth for transferred structures in the range of a few micrometers or so. But sometimes even deeper structures would be required. So again, our customers at EPFL have been working on a process that can be used to amplify the structures. And in this process, an intermediate hard mask material is added just underneath the PPA PMMA stack between the on top of the substrate. In the etching process, so in this case, silicon dioxide has been used, and the structures from the PPA has been transferred to the silicon dioxide first using helium hydrogen C4F8 process, and then the silicon dioxide acts as the hard mask for the next etching step, where the transfer is carried out using either array or deep reactive ion etcher and our common silicon etching chemistry SF6C4F8. And in this case, of course, the selectivity between the silicon dioxide and the silicon is much larger than selectivity between PPA and silicon dioxide or PPA and silicon, and we can achieve much larger amplification of the patterns. In these couple of example images, so first 35 nanometer deep patterns in PPA were patterned, and after the etching into the silicon dioxide and then further to the silicon, up to 4 micron deep patterns were achieved. And here's another design that was also transferred, and here's a cross-section image showing several micron etching depth, starting from a few tens of nanometer patterning depth. So we can actually amplify the depth of the patterns by a factor of in excess of 100 using the intermediate hard mask approach. Now, unfortunately, not only the depth of the patterns is amplified, but also the defects and surface roughness. And towards this end, they developed an ion beam polishing approach, which uses a gentle argon ion beam for polishing the substrate after the reactive ion etching process. So here, the argon ions have a small energy of only 700 electron volts, which is relatively small. And using this approach, they were able to reduce the RMS roughness of the surface from the 3.3 nanometers just after the reactive ion etching to about 1.2 nanometers after the polishing by the argon beam. Another even more efficient approach is to actually coat the sample with a thin layer of PMMA just after the reactive ion etching, and then apply the ion beam polishing in a process which is called polymer-assisted ion beam polishing. And using this approach, they achieved even more smoothing. So from the original value of 4.2, they went to less than 1 nanometer in surface roughness. And so why does this kind of polymer coating then help in smoothing the surfaces? So first of all, it will fill any recesses we have, so kind of thinerize the surface. So we have a more uniform surface erosion, so we don't have difference between the erosion at the top and the bottom of the structures. We will also have less erosion from reflected ions, as the reflected ions will be then captured by the PMMA layer. And also for the same reason, we have less redeposition of sputtered material. At the end of the process, the PMMA is simply dissolved in a solvent, and the smooth surface is revealed. I would like to present another technique for transferring 3D structures called the template stripping. This was developed at ETH Zurich. It will be published very soon by research carried out by Nolan Lassalin. So what we can see here is it's a sine wave pattern that we already saw on one of the very first slides. Not exactly the same, but the same kind of geometry. And it has been transferred in silver. So how does this process work? So first of all, we have a structure made, the sine wave structure, in resist, or it can be also transferred in, for example, silicon. And after that, a very thick film of silver is evaporated, or can be actually any material that can be evaporated, as I will show on the next slides. The important thing is that it's very, very thick, so that it's fully and conformally coating all the parts of the structure. And after the evaporation, a glass slide as a rigid support is glued on it using an epoxy adhesive. And when the epoxy adhesive has been dried and cured, we can just mechanically peel it off and strip it, hence the name of the technology. And we get an exact replica of the pattern in the original resist or silicon. And this is the kind of nice quality you can achieve. And it's matching exactly, as we can see here on the AFM profiles at the bottom right. The desired profile is matching exactly very well with the profile in the silver after the stripping, as well as in the etched profile in the silicon, and also the written profile in the PPA. And in this case, the amplification from PPA to silicon has been 4.2. Another example of a sinusoidal grating in silver, a very nice example. The same approach can also be used to replicate structures into titanium dioxide, so the electric material. So in this case, a pattern like this was applied. That was first etched into silicon using a process that gives us 1-to-1 selectivity. Afterwards, a layer of gold was evaporated on top to act as an anti-stick layer. As we know, the adhesion of gold without any kind of adhesion layer is quite poor on silver. On silicon, and that's why it can be used to help releasing the structures. And afterwards, a thick layer of titanium dioxide was evaporated on top, and it was stripped mechanically using the glass slide, glued on it with epoxy adhesive. And finally, the gold was etched away using aqua regia. And here we have the replicated structure, of course, a negative image of the original structure. And last but not least, I would like to also introduce the electroplating process for 3D pattern transfer. So here the approach is again relatively simple. So we start with PPA on a substrate, for example, silicon substrate, and we pattern the desired 3D shapes on it. In this case, we have to evaporate a thin seed layer just to act as a starting point for the electroplating process. And then we immerse the sample in a electroplating solution. So maybe here it's worth pointing out that the PPA itself is chemically not very stable in acidic and very strong basic solutions. But adding the the seed layer here, which can be nickel or can be chromium gold or something like that, it really helps to protect the PPA from degradation. And we can carry out a nickel or, for example, nickel plating process. And in the end, we can dissolve the PPA in a solvent, or we can just heat it up. And we can, if desired, we can also add a backplate to support the nickel structure at the end. And here's an example of a structure that has been electroplated. So this is a topographical map of Switzerland that has been coated plated into nickel, and we can see very nicely how all the hills, the mountain tops, and the valleys are replicated in it. Then this kind of nickel masters can be used as templates for injection molding. So injection molding is a technology. It's a very, very high throughput technology. It's commercially used to make precision plastic parts in the, let's say, tens of thousands, hundreds of thousands per hour volume. So here we simply insert our insert. It can be the nickel master in the cavity. Everything is closed very tightly, bolted together, and then polymer is inserted in the cavity with high pressure, and the polymer replicas are produced in the other side, and they can be removed from the process, from the apparatus in the middle of the process, and the next one can be injected immediately, hence the very high throughput. And here on the bottom right, we can see an AFM image of a final structure that has been replicated in plastic. And actually, all the topography is again reproduced extremely nicely, again taking into account that how fast and how high throughput process this is and how small all the features are. With this, I would like to conclude. So you should remember that NanoFrazor is capable of uniquely precise 3D grayscale patterning. That's thanks to the closed loop lithography principle and a very powerful feedback algorithms within the software. Now the patterned precise 3D structures can be transferred to underlying substrates using standard reactive ion etching processes. And of course, if the PPA is alone is not enough as an etching mask, then also it's possible to first etch it to another material that will enable to achieve depth amplification. So we can achieve amplification in depth of up to 100. I also introduced a template stripping approach, which can be used to replicate structures in materials that can be evaporated, and electroplating process that can be applied to materials that can be electroplated. And finally, the NanoFrazor process handbook that is available in the NanoFrazor software contains much more detail on all these processes, also including example recipes that can act as a starting point for process development at our customer sites. And of course, we are available to support you with all your process development at any time. So thank you for your attention, and I look forward to answering your questions.